Okay, so here's the implicit function theorem we were talking about. And I want to draw your attention to a certain point of view on what happened here. And notice there are in fact two variables, x and y, and arbitrarily I was choosing I wanted to view y as a function of x. When I said I wanted to view this as a graph, hey, I can't view this as a graph here, but I can here. And this is all with the understanding I want to view y as a function of x. Okay, so looking at this picture, it's because I wanted to view y as a function of x that the verticality of this tangent line is the problem. Right? Well, that verticality of the tangent line is, okay, that connects to this being horizontal, which connects to this being a partial derivative with respect to y. So ultimately, the variable that you want to view as being a function, that's the one that you have to take the partial derivative with respect to. So I would encourage y'all to give it a try. Try to make an argument that would be along these lines, analogous to this. What would the picture look like of there being a problem in your hope to be able to view x as a function of y? What would that problem look like? What would that consequential tangent line look like, and the gradient vector? And then what would what you'll find is that the issue would be in the partial of f with respect to x. Okay, so something to keep in mind. There is a very analogous result in multivariable. So this, why did I spend a bunch of time cleaning up? I mean, our goal here is not to clean up single variable calculus. Our goal is to understand some multivariable calculus. And so in this multivariable setting, here's a picture of problem that we might consider. Maybe we're looking at some surface instead of a curve. Now a level set. Right, so f, some function capital F is a constant. Some function capital F of x, y, and z now. Well, at a lot of points, like maybe over here, locally, not globally, we have to erase this part of the surface, but locally, near a point like, say, this one, I can view z as being a function of x and y. No problem, right? Just, don't go very far, don't venture very far away from there, and it's fine. Where can't I view z as being a function of x and y? Well, at points that have a vertical tangent plane. Right? This is just an appeal to your geometric intuition, but the problem would be if the surface were wrapping under itself. Then that would be why I would fail the vertical line test no matter how close I get to the point. So it is the fact of it wrapping under itself, which, in other words, it's the fact of there being a vertical tangent plane. Right? That would be the sign of a problem. That vertical tangent plane would mean that the gradient of my capital F would be horizontal, namely that it's z partial is 0. Turning it around again, of course, then if the z partial is not 0, then there's no problem, and yes, I can view z as a function. So it's always whichever variable you want to view as the output variable, whichever variable you want to view as being a function of the others, it's with respect to that variable that you have to make sure the partial is not 0. Okay, so here's the statement of the theorem, and there's a lot of discussion in here, but the big punchline is, if you're looking at a level set, if the partial with respect to one of those input variables, y in this case, one of the input variables to that level set equation, if the partial with respect to that input variable is not 0, then that variable, whichever one whose partial is not 0, that variable can be thought of as a function of the other variables. Just like in the single variable case, yeah. Well, that's the confusing thing, isn't it? So let's look at this y thing. Y is an input variable to the capital F function. Yeah, right? But I want eventually to view it as an output variable of, its own function. I want it to be a function of the other variable. So it's, it starts off as an input variable. I would like to be able to reinterpret it as an output variable. Yeah, right.
Okay. All right, so here is an example of how we can use that. Now, here's a surface that even though I can kind of approximately, that's not entirely unlike a sphere, sort of, kind of, in a way, qualitatively. But it's not exactly a sphere. I don't really know exactly what this surface looks like. But I can ask, at this point, how would I find partial of z with respect to x? Or can I find partial of z with respect to x? I phrased this as what's the slope of the tangent line to the cross-section of the surface perpendicular to the y-axis, and think through the geometry of that, and that means, hopefully, fingers crossed, can I compute partial of z with respect to x?
Well, now, before I proceed, I've got to ask, does that even make sense? Is z even a function? That's the big worry here. Is z a function, or is this meaningless nonsense? And if z is not a function, you can't take a derivative of it. You can't take a derivative of a bicycle, and you can't take a derivative of a beach shovel, and you can't take a derivative of a letter of the alphabet unless it's actually a function. So how do I establish if z is a function?
I'm going to establish that by taking the partial with respect to z of the function whose level set I'm looking at. Here, let me do a better job there. The function whose level set I'm looking at.
You could always leave the 3 on that set, right? Instead of
yeah, if you want to take this, 3 and move it over, you can. But the first thing we're going to do with this function is take a derivative of it, right? So whether you take the 3 over or not, it doesn't really matter. In previous examples, I did just because I had all of my previous work set up as f equals 0, and so I just figured to be consistent. But it doesn't. You're quite right. It doesn't really matter. Yeah.
Right. Okay, so we take that function, take a partial with respect to z, because z is what I want to view as being a function of the others, and plug in the point in question. We're interested in what's happening at the point 1, 1, 1. Plug in 1, 1, 1, and not 0. Therefore, not a problem. Yes, you can view z as a function of x and y. Everybody okay? Yep.
Do you always use this with level sets?
Yeah, very importantly, it's a couple different points of view on that. We're looking at equations, and all equations can be written as level sets, right? As we noted a long time ago. But also, we have to. It's because this is a level set that I know that the gradient is perpendicular to it, and that's the foot in the door that makes the theorem work. Yeah, so it's got to be level sets. Yeah. Okay, so not 0, therefore no problem, and therefore we can just start taking an implicit derivative. So let's look at this equation. Now, do be careful. We got to keep in mind about what variables are playing what roles here. I have now decided to view z as a function of x and y. Right here, let me write this down. We're viewing z as a function of x and y, so z is a function. Let's see here. By the way, we were interested in computing the partial of z with respect to x. Okay, so x is going to be our variable that we're going to take a derivative with respect to. And then what about y? What is y doing? Well, we're taking a partial derivative of z with respect to x. That means that z, this function of x and y, I want x to be the only variable. That means y is going to be a constant. All right, so all three of these variables are playing different roles now for the purposes of this next partial derivative calculation. Z is a function. Don't forget to use the chain rule. X is the variable that I'm taking the derivatives with respect to. Y is a constant. So one term at a time, you can take these derivatives. Let's see here. The derivative of x squared with respect to x, 2x. The derivative of y to the fourth. Okay, well, don't forget, y is a constant now, right? So z is a function of x and y, partial with respect to x. That means y is not changing. So that partial derivative is 0. It's real easy to mess that up and write 4y cubed. Know what I mean? Or 4y cubed dy dx. Some students might, more responsibly want to write. But importantly, y is a constant, and so it's just 0. And then what is the derivative of z to the 6th? Well, here's where the chain rule kicks in. Z to the 6th is a function of z. Z is a function of x. Taking a derivative with respect to x. So we get this product is 6z to the 5th times dz dx. Yeah.
Are you saying y is a constant because the surface is perpendicular to the y-axis?
I am, let's see, where did it go? Yeah, so perpendicular to the y-axis is why I'm interpreting the answer that I'm looking for as partial of z with respect to x. Because as you're moving, let's see here, x-axis, y-axis, if you're moving perpendicular to the y-axis, then you're moving in the direction of the x-axis. Yeah. Does that make sense? Mm-hmm. Yeah. Just as it did in the... Oh, I'm sorry. Go ahead.
I also could have done partial of x with respect to z, right? And then just flipped it and then checked that that's not 0.
Well, what we needed to compute is the partial of f. The thing that needs to not be 0 is the partial of f with respect to z.
But say I had done partial of f with respect to x.
Okay.
And then I can do partial of x over partial.
So you're saying, well, see, you're stepping into deep water there. So here's the problem. So if you take the partial of f with respect to x, and then compute the partial of x with respect to z by a method not unlike this, right? Then what you're saying is, I'm going to view x as a function of y and z. You can't then, just by virtue of taking a derivative, infer that z is also a function of x and y. It's just, that doesn't follow. You see the problem there? I mean, again, we're not just manipulating symbols, we're making interpretations, and the interpretations are tougher there. So, yeah, I don't want to venture into that. I think that's hard to conclude. I think the line of reasoning there is fraught. Yeah. Is that cool? Yeah. Okay, so now having done this derivative, notice that we have an equation in which the thing that we're interested in has showed up. Solve for it. Everybody wins. No problem. Okay. All right. Okay, moving along. Now, we are temporarily done with Chapter 4. There are 3 sections left. There's 411, 412, and 413 left. I'm going to skip them and come back to them later. When I was writing the schedule for this course, it slipped my mind that I wanted to make this little jump. We are going to do this material. We're just going to do it at the end of the course instead of here in the middle of the course. There's a long story as to why that is. The short version is Chapter 6 is a very challenging chapter, and it's better to get to it as quickly as possible. The quicker we get to Chapter 6, the quicker we finish Chapter 6, and the more time that y'all have to then absorb and digest and chew on, etc., Chapter 6 and make sense out of it before the final exam. And I think there's a lot of benefit to doing that, right? So, sadly, the vast majority of the material in this course is prerequisite to Chapter 6. It's a very vertical course, okay? So, these last 3 sections of Chapter 4 are, golly, about all that I can put off until later to this end. So anyway, that's what we're going to do. I'm going to need to go in and edit the all the projected page numbers that I have in the lecture schedule. I'll see what I can do about that. But anyway, we're going to come back to these 3 sections later. So for the moment, we're going to skip ahead now to Chapter 5. and go from there. So I have a little discussion here that I want to talk, a little preliminary discussion about single variable integrals. We're moving into the chapter on integrals, by the way. Multivariable integrals, as I often do, we're gonna segue into talking about multivariable integrals by talking about single variable integrals a little bit. And there is one pretty common problem that I've bumped into in teaching this course for several years now, and that a lot of students have a very severe misunderstanding of what single variable integrals are in a very fundamental way. And I know y'all are really good at computing this stuff, right? But in terms of, fundamentally what is an integral, a lot of students have the mistaken idea that integrals are the area under a graph of a function. And this is something that happens to be true usually in conditions, and let's not worry about the fact when it dips down below the x-axis. That's not what I'm talking about. But the big point is that's not what the definition of an integral is. Another misconception: a lot of students think that this function, the function whose derivative is little f, that's an integral. And that's some unfortunate terminology. And from a point of view of a definition, as we're defining integrals going into Chapter 5 here, we, and very importantly, cannot conflate the word integral and the word antiderivative. This capital F here is an antiderivative. It's not the same thing. Last misconception. A lot of students think that this is the definition of an integral. The integral from a to b of little f of x dx is, by definition, capital F of b minus capital F of a. Also not true. That's a theorem. Under certain conditions, that's a formula for computing the integral, but that's not the definition of the integral. So, I want us to get all on the same page here as to what the definition of an integral is. That's the definition of an integral. It's a Riemann sum. And it's important that we choose to view integrals as Riemann sums, and most fundamentally, for a combination of reasons. The one that I'm not going to try to persuade y'all of is from a mathematical rigor point of view, conceptually, that this is important for reasons of rigor, because I know this isn't a pure math class, and I would love that conversation, but it's not something that would really be appropriate in Math 212. What I'm going to try to persuade you with is a different point about why Riemann sums are not only critical in this discussion, but importantly must be the definition of an integral for the purpose of applications. So here's why. Yeah, I know computing the area under a graph is something y'all have done a million times in Calc 1 classes. But I ask this question. In your outside of Calc 1 classes or Calc 2 classes, how often have you really had to compute the area under a graph? Pretty much never. Right? I was a double major in math and physics in college, and it was pretty rare. There were a couple instances where it happened. Peculiar. But outside of calculus classes, it was actually pretty rare that I needed to compute the area under a graph, between the x-axis and the graph. It just almost never happens. But why do we talk about it so much? Why do we talk about in calculus classes, we got to compute the area under this graph? Ultimately, it's because this is the most geometrically convenient picture we can draw of what we're really actually interested in, and that is Riemann sums. Alright? So there's a geometric satisfaction in, I see the picture, and this is that, and that's that. Everything I see in the algebra, I can see on the picture, and it's comforting, right? And it's intuitively pleasing, and that's all fine. I'm all for that. But most importantly, what is an integral? That's not that. Riemann sums are what's important. Now again, so what's the pitch? Why are Riemann sums so important? It's because of all of these other applications. And you'll notice I left this circle unclosed here. This is deliberately open. There are, as you probably know, tremendous numbers of applications of single variable integrals. It's just endless, right? There's so many different applications, and there's a few that we kind of more typically deal with because they're a little kind of easier to get our hands on. How much work does it need to fill it? Y'all remember the tank filling problems, right? That's a pretty real scenario of like energy is money. Right? How much energy it's going to take to actually pump, water or gas or whatever it is into a tank? It's going to cost us, man. We need to know how much that is. That's a big deal. How much does something weigh when the mass is non-uniform? When the mass density, is non-uniform. So it's this distribution of mass is not constant. Various other applications. How do we get our hands on these applications? And the answer is, in all of these cases, and in many, many, many other cases, it's not that we understand a tank filling problem by interpreting it as an area. That's not the point. What we can do is we can take a tank filling problem and I can write the answer to that question as a Riemann sum. If I need to compute the mass of some sort of a one-dimensional rod that has a non-uniform density, I can write its total mass as a Riemann sum. And area doesn't have squat to do with it. It just doesn't. So this is the connection between a tremendous number of applications and the fundamental theorem of calculus, the tool for computing integrals that allows us to actually turn Riemann sums into answers. The essential connection between the question and the answer is the construction of the Riemann sum. So this is a really big deal. We're going to see this continue to be the case in multivariable calculus. Now, a lot of you might be thinking, so I'm just going to, one last comment and then we'll move along. A lot of y'all might be thinking, well, yeah, but I think of this, the mass of a rod by, look, you're taking density, mass per unit length, you're taking that density and you're multiplying it by a width of a little piece of the rod, and if you just think of the density as being a height, then you can think of density times size as being height times width, and so you can think of it as an area. So let me point out what that, and I get that, and that's satisfying also, right? But what you're really doing there is you're saying, well, this, if I kind of interpret it as a Riemann sum, then I can think of it as an area. And then, and then if I choose to think of areas as integrals, then I can fundamental theorem and I can get an answer. But I just want to point out how perverse this is. There's no need for that. Right? You don't need to be able to think of it as area. And if you like thinking of it as area, again, knock yourself out. It's harmless, I suppose, right? But the only way that you can reinterpret a mass question as an area question is by breaking it down as a Riemann sum and observing that Riemann sum can be reinterpreted as area. There is no immediate connection here. Right? Minus Riemann sums, there's no way to relate mass to area in that context. So Riemann sums are unavoidably essential in these discussions. Okay, all right, enough of that. So here's Riemann sums. This is what they look like. I hope you all remember seeing these before. Oh, by the way, if you have not seen Riemann sums before, then it's definitely something you want to make sure to look at, and come talk to me, and we can talk about how to find some resources on that. Okay. Okay, so a couple of examples of how we would use Riemann sums. Here are some applications. We talked about area under the curve, and again, that's a nice application of integrals. Sure, fine. If you have some curve like that, and sitting over this interval on the x-axis, you want to compute the amount of area, right? Well, you can make a Riemann sum by chopping up this interval into little slices. On each slice, we talk about the amount of area in that slice. I interpret that area as being height times width. I look at these products, height times width, and I add that up over each piece, and there's my Riemann sum. Okay. Here's a different application. If I have this rod here of non-constant density, so maybe it's more dense over here and less dense everywhere else. Right? Some sort of a weird sort of alloy mistake where they poured in too much iron on this side and too much aluminum on this side. I don't know. How do we compute this total mass? Well, we're going to take this interval representing this rod. We're going to chop that interval up into little pieces of width delta x. On each little piece, we acknowledge that the amount of mass actually inside of that little piece is density times length. Right, so density in this context means mass per unit length. Mass per unit length times length would give you the amount of mass in that little piece. Round off errors, sure. And then if you add up how much mass there is in each little piece, if you add that up over all of the pieces, you would get the total mass. And notice two very important things here. What I just described is a Riemann sum of, function times delta x summation as I goes from 1 to n. That's a Riemann sum. And 2, no area anywhere in that discussion. Right? This is not about computing the area under some curve. We really have to want to view it this way to view it that way. Right? And I encourage not viewing it this way because it's not part of the problem. It's not necessary, and it'd be good to let go of that. It's kind of a crutch. I mean, at some point, students depend too much on this idea of viewing integrals as being area under graph. It will become a problem a little bit later on. Pretty soon, at the pace we're going, it's going to be a problem soon. So try to think of this application here as not having anything to do with areas. It's just a physics problem that we rewrite as a Riemann sum, aka an integral. Okay, so all right, so I'm done with my complaints about Calc 1. What I want to do now is ask how can we generalize this construction, this strategy you might call it. How can we generalize this into a multivariable setting? And let's just take a step back momentarily and remember we've faced such a question before. We talked about derivatives, right? Derivatives. We had an idea of what a derivative was in a single variable setting, and well, if we're going to generalize that, if we're going to extend that to a multivariable setting, we had to ask, what is it really? What is it about a single variable derivative that is a derivative, as opposed to just the peculiarities of the single variable context? And we came up with this idea of it's a relationship between input changes and output changes, and then much discussion ensued. So likewise, what is it about single variable integrals, a couple of examples of which we're looking at here? What is it about this that is intrinsic to the idea of an integral as opposed to just being the peculiarities of the fact that I'm doing it in a one-dimensional context? And so here's what I've come up with. This is a way of thinking about it. These rules that I've written down here, these criteria, are going to actually apply to all of the integrals that we're going to define in this course. By the way, we're going to define a bunch of different kinds of integrals over the next couple of weeks. I lost count. I think I remember at some point counting 9 different kinds of integrals. They're all going to have, in their own ways, all 4 of the properties that we're about to write down here. So here we go. So for each of those examples we just looked at, there's something called the domain, and there's a function called an integrand. So here in the area question, there's the domain, there's the integrand. For this mass on a rod question, there's the domain, there's the integrand. It's density, not height. Different integrand. But it's the integrand defined on the domain. Okay. Second thing, I can chop up that domain into little pieces, and what I'm actually interested in is a sum over those little pieces. All right, so what do I mean by that? Well, I can take this interval and I can chop it into little pieces. And furthermore, the thing that I'm interested in is a sum then over those little pieces. So if I look at the amount of area over a little piece of the interval, if I add up these individual pieces of area, I get the total area. Looking at this bottom example, if I'm interested in mass, if I chop up this interval into little pieces, the total mass that I'm interested in is, in fact, the sum of the little masses that I get on side of each little piece. Now, I claim this is a non-trivial and a critical point. And a lot of students will look at this and be like, well, yeah, but, well, of course, isn't that, I mean, what, come on. But keep in mind, we're not simply asking what's going on with these two examples. We're asking what is intrinsically part of the strategy that we're using to address these questions, right? And we are intrinsically using the fact that total mass is the sum of a bunch of little pieces of mass. One of the things that makes the mass of a rod question susceptible to the integration strategy is the fact that mass is this accumulated kind of quantity. So let me just point out that not every calculation you'll ever want to do in this life is necessarily an accumulating quantity. For example, centroid, right, let's say average, center of mass, whatever you want to call it. That's not an accumulating quantity. You could very reasonably want to compute the center of mass of this rod. It is not the sum of the center of mass on that piece plus the center of mass on the next piece, right? It's just not. Yeah? Okay, so be careful about, what assumptions are we really making when we say we're going to do an integral. We are unavoidably confining ourselves to addressing questions, quantities that have this feature of accumulation. So keep that in mind. Okay. Let's see here. Third. This is kind of a formality, but the integrand is approximately constant on each piece. We have to say it's approximately constant on each piece for a couple of reasons. I need to be able to say, well, then on this little piece right here, the mass is density times size. Well, that density, if it's not exactly the same everywhere in there, I at least need them to be pretty close to the same. Otherwise, which value of density do you pick, and you have severe problems with round-off error. So I don't need the integrand to actually be constant. I just need it to be I need it to be nearly what we're eventually getting around to saying is I need the function to be continuous. If I want to say it in a more relatable way, that as these pieces get smaller and smaller, I need that integrand to be, approaching roughly constant. Okay. Lastly, and again, this is intrinsic to the strategy that we're taking in doing integrals. On each little piece, we're looking at a product, and that product has as its two factors the size of the piece and the value of the integrand. So let's look at these applications again. The things that I'm adding up here, looking at the area question. This area is the size of the piece times the value of my integrand. My integrand was the function whose graph I'm looking at, namely it is the height. On this mass application, What am I adding up here? This is the amount of mass inside of that piece. Well, it's the size of the piece times the value of the integrand. Length times mass per unit length. So all examples where you've done integrals in the past, all four of these properties hold. We don't really think about it in those terms most of the time. We just kind of write them down. But we always have a domain and an integrand. You can always break it up into smaller pieces, and you have this accumulating characteristic. Regularity issue about continuity. We usually sweep that under the rug. And then we're always looking at products of size times integrand. Okay. Now, I want to draw your attention to something that's conspicuously missing from these four properties. Conspicuously absent is the idea that size must be length. Right? That the domain must be one-dimensional. The domain must be an interval on the x-axis. It's not on the list. Right? Every integral we've seen in the past, we were looking at an integral over an interval on the x-axis, t-axis, x-axis, whatever. A one-dimensional domain, and that when we chop it up, those pieces have a one-dimensional notion of size, namely length. Deliberately left that off, because that's the foot in the door that we're going to leave open to us to doing something in higher dimensions. So we're, roughly speaking, going to take other kinds of domains. We're going to start with two-dimensional domains in just a couple seconds. Two-dimensional domains. We're going to break them up into pieces. Size is not going to be length. If you have a two-dimensional thing, size means area. Okay, but even in those, in the extended, version of this in a multivariable context, we're going to be taking our domain, chopping up the little pieces. We're going to be relying on the fact that our quantity in question is a summation of the quantities on each little piece. And on each little piece, we're going to be looking at some function times size, which will no longer be a length. Okay. All right. So anyway, for all the integrals that we're going to define, 9 different kinds of integrals that we'll define over the next, couple weeks. Look for these 4 properties. Okay, so let's get an example done. Now, as much as I kind of trash talked the question of area under a graph, the very first example I want to do of a double integral, which by the way I have not defined yet, we'll define this after we do this first example, is I want to look at a graph. It is, after all, very visually satisfying, right? Thinking of single variable integrals as area under a curve, super satisfying. It's a fantastic starter example. First time you see integrals, yes, I think it should be about area under a graph. I'm a big fan for sure. So we're going to look at a graph here. Now a function of 2 variables. Z is a function of x and y. And I want to consider sitting over some rectangle. Now, not an interval. Sitting over some rectangle in the domain. Let's ask how much volume. How much volume is there sitting under that surface? And you can see how this is kind of analogous to area under a curve. So, can I use an integral for this problem? Does this have those features that I was describing? Let's go through them one at a time. Can I take this question, can I take the domain and chop that domain up into little pieces? Sure. Here we go. Here's my domain, and I'm going to chop it up into little pieces. I've got to kind of double chop, if you will. I've got to slice that way, and then subsequently I've got to slice that way. But if you slice both different directions, you get a bunch of little pieces down here. And these little pieces, there. I mean, there's bazillions of little pieces that you can chop it up into. Again, you have to dice it. These long, skinny strips are not okay, right? I've got to chop both directions. Is it true? Now, beware, not every question in life has the following property. But is it true that if I look at the volume sitting over each individual little piece, if I were to look at all of these individual volumes, and if I were to add over all the little pieces that I chop the domain into, I appeal to your geometric intuition, is the sum of these individual volumes going to give me the total volume? Yes, it does. Right? So that's something we need. If I want to mimic the integration strategy that we used in the single variable context, that better be true. And for this question, for the volume under a graph question, it is true. You just think about it in terms. I like to think of like a. Imagine you have a big potato. Right? Somebody's chopped the bottom of it, so it's got a nice flat bottom on it. You got this potato. Forget about the bottom half, right? So here's a potato. If you take that potato and if you chop it that way, and if you chop it that way, you've got a bunch of French fries. And the total volume of the French fries is the volume of that original chunk of potato. Plausible? Okay. All right. Next question. Is it true that the volume in each little piece, is that equal to area down here, size, times some function, and in this case the function is height? And again, good news. Yes, thankfully. Volume is the base times the height. That height, you notice, of course, being the value of our integrand function. Height is z, z is f, therefore height is f. So all of our conditions are set. There's the regularity thing, is this function approximately constant on each little piece? Well, look, what I really need here is for this function to be continuous. So we're gonna assume that this function is continuous, and I appeal to your intuition about continuity. If you look at teensy-weensy, itsy-bitsy little pieces, then it's not going to be exactly constant, but it's going to be close. And at the limit, the rounding errors are going to go away. All right. So conditions are satisfied. We have here a question which is susceptible to the integration strategy that we previously talked about. And there's a certain amount of little detailed devils that we're going to have to deal with. I'm going to have to figure out how to quantify, what are these little pieces. You may recall from Riemann sums a long time ago that there's formulas like delta x is b minus a over n, and xi is a plus I delta x. Do y'all have faint memories of all this stuff from long, long ago? Okay. If you haven't seen this stuff before, come talk to me. It'd be a good thing for us to kick around in office hours. But we're going to need to do sort of a double integral version of that, and what we're eventually about to write down is a Riemann sum that's called a double integral. But we're out of time for today, so we'll do that Monday. Tuesday. Oh, yeah. Oh, we have a long weekend. Cool. Right. Great. See y'all Tuesday. Well, I'll see you in office hours, but after that, see you Tuesday.